Okay, so now we move on to the next part, okay, where we talk about something called logical binary shifts. Okay, so this is where we will be shifting binary numbers by a certain number of steps. Okay, so if you go through the first point, it says computers can carry out logical shifts, okay, on a sequence of binary numbers. Okay, so on a sequence of binary numbers, the computer can move those numbers according to a certain number of steps. Okay, I'll explain that to you. Okay. So the logical shift means, so what do you mean by a logical shift? We move the binary numbers either to the left or to the right. Okay, that is what we mean by a logical binary shift. Okay. Now, if you are to shift to the left, okay, so over here it says each shift left is equivalent to multiplying the binary number by 2. Okay, so every time you shift a binary number to the left, okay, you have to multiply the value by 2. Okay, the original value that you have, you just multiply by 2, it will give you your new value. Okay, it will give you a new decimal value. Okay, however, if you shift to the right, if you move it to the right hand side, it is equivalent to division or dividing the binary number by 2. Okay, so the sequence of binary numbers, if you shift it to the right, okay, each time you shift it to the right, you divide the original answer by 2. Okay, so that will give you the new decimal value. Okay, the binary's new decimal value will be given to you. Okay, also in the final point it says, as bits are shifted, as you move these bits, these zeros and ones, as you move them either left or to the right, any empty positions are replaced with a 0. So when you move the binary digits to the left or right, wherever an empty position comes up, for that empty position you will be simply putting a 0. Okay, so I have given you a brief explanation of what logical binary shift is all about. Now let's take an example and let's see how it works. Okay, so if you look at the first example that has been given over here, we are dealing with the denary number or the decimal number 21. And this decimal number 21 is equivalent to the following binary number. Okay, so if you were to convert this decimal number 21 into binary format, this is the number that you would get. Okay, let me undo that. Okay, this is the binary number that you would get. Okay, so now this binary number 0001010 has been put into an 8-bit register. As you can see over here, it has been put into an 8-bit register. This is how it looks. Okay, now if you look at step number 2, okay, if you look at the second step, what happens is if we now shift the bits in this register one place to the left. Okay, so we are now moving it one place. So this binary number, we are moving it one step to the left. Okay, so if you notice what happened is this 0 has now got cancelled. Okay, it has been pushed out, it has been moved out, and this 0 has moved forward, this has moved forward. So everything over here moves forward, and you can see that answer over here. Okay, so as you push everything one step to the left, as you push all the binary digits one step to the left, what happens is you will have a blank space over here. You're going to have an empty space over here. Logical, isn't it? When you push all of them to the left, there's going to be a blank space at the end. So like I told you, okay, wherever there is an empty position, we fill that with a 0. So that's exactly what we have done over here. We have now put a 0 in the empty position. Okay, now if you recall, at the beginning I told you, each time we multiply, okay, each time we shift to the left, we have to multiply by 2. Okay, so in this example, we have shifted only once. Okay, we have only shifted once, which means we have only shifted left once, which means we need to multiply by 2. Okay, so the original value was 21. That's what I have written over here. Originally we had a value of 21. Now that we shifted it left once, we have to multiply it by 2. Okay, so 21 times 2 is equal to 42. Okay, so if you were to convert this decimal value, which I'm marking over here, these decimal values, okay, if you were to convert these binary values into decimal, you would get the value 42. Okay, so this is how a left shift works. Okay, I hope it makes sense to you. Okay, let's go on. Okay, so now what we are going to do is we are going to try shifting it 2 places. Okay, the number 21. Okay, this number 21 over here, we are now going to try and left shift it twice. Okay, so by now you should be telling me, once you shift it twice, then what happens is you should take 21 times 2 times 2, or 21 2 squared you should take. 21 multiplied by 2 squared you should be taking. Okay, right, let's see what happens over here. Okay, so again, I'm repeating, we are taking the original value of 21, the binary value of 21, and we are now shifting it left twice. Okay, so this is the value that we have got. Okay, so once we push it to the left twice, this is what's remaining. And then we have two blank spaces over here. Okay, so for the two blank spaces, like I told you at the beginning, we fill the blank spaces with 0. Okay, we fill the blank spaces with 0. Now, since we did a left shift twice, we take the original value of 21 and we multiply it by 2 squared, because we shifted twice. Okay, left shift twice, so you multiply by 2 times 2, or 2 squared. Okay, so now you get the value 84. Okay, so you can either multiply and get 84, or you can simply convert this binary value, convert it into decimal, and you would get 84. Okay, but of course, this method is much faster. You take the original and multiply it by 2 squared, you get 84. That's much faster than converting this into decimal and then getting the value. Okay, right. Now, there is only a certain number of times that you can shift a binary value. There's only a certain number of times. When I give you a binary value, there is only a limited number of times you can shift it. Okay, so what is that limit? That's what we're going to look at now. Okay, so let us consider what happens if we shift the original number 21, okay, which is this binary value. What happens if we shift it 4 times? Okay, we are left shifting it 4 times. Okay, so when you left shift it 4 times, the original value of 21, the original binary value of 21, when you shift it 4 times, what happens is you lose a 1 bit. Okay, so look over here. This moves, this moves, this moves, and this also moves. The moment a 1 gets pushed out of the register, that's when you have reached a problem. Is it clear? So listen to me again, okay? You can shift it as long as zeros are being pushed out. That's all right. But the moment you touch a 1, the moment a 1 is pushed out, that's a problem. Okay, so as long as you're not pushing out any ones, that's not a problem. Okay, so just keep this in mind. So we are going to have a problem here because a 1 is being pushed out of the register. So now we will be getting a problem. Okay, so as you can see, it says the leftmost 1 bit has been lost. In our 8-bit register, the result of 21 times 2 to the power of 4. I hope you do understand why we are taking 2 to the power of 4. We're taking 2 to the power of 4 because we left shifted 4 times. Okay, so when we logically do it, 21 times 2 to the power of 4, it should be 80. Okay, which is clearly incorrect. Okay, but we are not getting 80 when we convert this into decimal. We don't get 80. Okay, so this error is because we have exceeded the maximum number of left shifts possible using this register. Okay, so the reason that this error is coming up is because we have exceeded the maximum number of left shifts. Okay, so do keep in mind, you can left shift as long as you do not touch, as long as you don't push a 1 out. The moment you reach a 1, you have to stop. Okay, you can push zeros out, but you cannot push a 1 out. The moment a 1 is pushed out, you're going to have an error. Okay, so do keep that in mind. Okay, so now I have been showing you how to do left shifts. Let's see what happens when we do right shifts. Okay, so you do know at the beginning I told you when we do a right shift, okay, what happens is we divide the original value by 2. Okay, when we left shift, we multiply. When we right shift, we divide. Okay, so if you are to come down, now we are taking an example of 200. Okay, we are taking an example of 200. Okay, and 200 written in binary. This is how 200 is written in binary. Okay, 1100 1000. Okay, this is how it's written in binary. And so we have put this value in an 8-bit register. Okay, this value we have put into an 8-bit register. Now we are going to shift it. Okay, we're going to shift it 1 place to the right. Okay, we are pushing it to the right. So automatically what happens is this 0 over here is going to be pushed out. Okay, this 0 over here is going to be pushed out of the register. And then what happens is we get a blank space over here. Okay, we get an empty space over here. So like I told you, whenever an empty space comes up, we simply put a 0 into it. We fill it with a 0. That's exactly what we have done over here. For this blank space, we have put a 0. Okay, Now, if you look over here, since we did a right shift, we now divide the original value of 200 by 2 to get the new value, which is 100. Okay. So since we did one right shift, we divide the original value by 2 and it gives us 100. If you convert this into decimal, you would get 100. Okay. So far, so good. Okay. Let's go further. Suppose we now shift the original number 3 places to the right. Okay. What happens if we shift it 3 places to the right? Okay. So this original value over here, we are going to shift it 3 places to the right. Okay. So the moment we push it 3 places to the right, we have 3 empty boxes. Okay. So like I told you, the moment the empty box comes up, you fill it with zeros. Okay. So that's what we have done over here. Now, logically, what happens is, since we did a right shift thrice, we now divide the original value by 2 of 200 by 2 to the power of 3, which is 8. So 200 divided by 8 to get the new value 25. Okay. So logically, we get the new value 25. If you also convert this into decimal, you would get 25. So no problem. It's working. The shifts are working. But what happens if we shift it 4 places to the right? Okay, so what happens if we shift this original value 4 places to the right? So you can already understand the problem that's coming up. If you were to shift this 4 places to the right, this is 1, 2, 3, 4. So you can see here we have a problem, which is a 1 is going to be pushed out. When a 1 is pushed out, you are going to get an error. Okay, so keep in mind, the moment you touch a 1, you have reached your limit. Okay, you're going for an error. Okay, so you cannot touch ones. As long as zeros are being pushed out, that's all right. You can do those shifts. Okay, so over here you can see when we do a four place right shift, okay, you can see the rightmost 1 bit has been lost. In our 8-bit register, the result of 200 divided by 24 is 12, which is clearly incorrect. Okay, so the reason that this error is coming up is because we have pushed a 1 out. We have reached our maximum number of shifts. Okay, so this is what we call binary shifts. Okay, so over here they have mentioned logical binary shifts, so you can say binary shifts. So these are basically where you have a sequence of binary numbers and you can shift the positions. Okay, and you will get a logical answer. Okay, but there is only a maximum number of shifts you can do, and like I told you, you can shift it as long as you're only pushing out zeros. The moment you touch a 1, you're going to get an error. Okay, so there are 2 ways to shift it. You can either shift it left. If you shift it left, then your new answer will be multiplied by 2 to the power of the number of times you move to the left. If you shift to the right, it will be your original value divided by 2 to the power of the number of times you shifted to the right. Okay, I hope it makes sense. Okay, so I have given you all 2 examples over here. Okay, this is just a very short part on what we call logical binary shifts. Next, we have a rather large part, which is known as 2's complement. Okay, next we have a rather large part, which is known as 2's complement. We will move on to this part now. Okay,